Thanks, Parag, for that gentle introduction. And thank you, ladies and gentlemen, for turning up for this. Not quite. You don't want my mobile? It's difficult to live without mobile. Yeah, I can't keep it outside. I'll forget. Okay, firstly, I thank the audience here for making it in this presentation despite the rains. So as the name suggests, it's going to be talk on mechanics, but it's going to have all the elements of a movie. It is a romantic story, but there is a tragedy embedded. I hope you see the tragedy. I will not be explicit about the tragic part. Let that be implicit. The comedy, I guess, would be explicit. So there are other elements which I could not find in a word. There is fear, there is religion, there is philosophy. Ample emotions are there in this story. So we'll get going. So God created Newton and Newton created the three laws. That's where mechanics starts for most of us. First law, taken from Craig and Merriam. You cannot dispute this. It is taken, quoted verbatim. Craig and Merriam is a very authoritative book on engineering mechanics. But just like any student is, I have been very choosy in picking out the excerpts. I will choose the excerpts which I want to read. I will choose the excerpts which I want to learn. And this is quote from that very authoritative book. And it says particle remains at rest or continues to move with uniform velocity, blah, blah, blah. I can mark that up. Second law, again from the same book. The acceleration of the particle is proportional to the resultant force. Mathematically, nice equation. The force vector is equals to mass times acceleration. Even if you doubt Craig and Merriam, the third law you cannot doubt. It's taken from Google. Okay, it's a very authoritative source. And Google says every action has an equal and opposite reaction. That's what I was taught. And that time there was no Google though, but for a long while I thought this is the third law in its entirety. But there are problems with these statements, as I found out. Hopefully I'll be able to indicate the start of the trouble. So here I am, disappointed looking guy. First question, everything is about particle, right? And what is a particle? And this word particle somehow gives us a feeling that it's small. And then the question comes, how small should it be? Okay, so this is a very strong argument against Newtonian mechanics, which has been put up not just by me and some anonymous writers in Google, but very, very respected people in mechanics have always looked down upon Newtonian mechanics from this aspect. And if you talk to my students of my class, I have actually posted in Moodle excerpts from a very respected book which I have read, and I have been educated from that book, but the author has staunchly come down on Newtonian mechanics just because of this idea of particle. And he goes at length in the preface to describe how small the particle should be is never said by Newton. So how can this be a fundamental law of nature? Contrary question is, are the laws no good for oversized, pot-belly sized person like me? Okay. So if it is not, then why should I study it, right? Other question, it talks about velocities and acceleration. Acceleration pops out from the second law, but then that depends upon the observer. And then Newton himself is saying that this observer is fixed to some distant star. Where is that star? I don't know. Okay, and Newton possibly did not know. So this is again another thing which makes me depressed in my first encounter with mechanics, that what is this distant star? Do I have to leave my earthly home and travel in space and time to understand Newton's laws or use them? So this is another part of the story. This is interesting. From second law, we get that if force is equals to 0, force is equals to mass times acceleration. So if force is equals to 0, for any positive mass, you should have acceleration equals to 0, no big deal. Acceleration equals to 0 means velocity is equals to constant, whether you take it 0 or some positive value, but velocity is a constant. But that precisely is the first law. So does that mean that first law can be derived from second law? First law can be derived from second law, in which case why is the first law in place? If that is not a fundamental axiom of mechanics, it does not deserve to be called a law, because it is a derived result. So therefore, arguing this way, we can find, and this is elementary mathematics, this is not anything to get scared about in terms of mathematics, just f equals to 0 would mean acceleration equals to 0 and v is constant, which is first law. So which means we have to raise a question that are the laws independent? And for Mr. Google's interpretation, does action, Google kept it as simple as this, that every action has an equal and opposite reaction. What it missed out was that action and reaction cannot act on the same particle. Okay? So this is an important attribute which is missed out in that statement of third law, which is also given in many, many different books. But I suppose Google is more authoritative than books, so I therefore wanted to quote Google rather than any book on this subject matter. So the question which pops up was this, that does the action and reaction act on the same particle? It does not, as you know. So we need to reword the statements of the first, second and third laws as we go along, which we will do in some time, but we will try to explain each of these controversies one after the other. Okay, immediately I would like to settle the issue about third law, and this is taken from a more respectable but not so widely read book. It is Classical Mechanics by Goldstein, written in 1960s, but obviously it has not found such high H index as Google has, so we'll leave it at that. And therefore, we'll state third law as stated by Goldstein. So it says the forces the two particles exert on each other are equal and opposite. It sort of trims out that dramatic effect of action and reaction and what not, but it states in nice and simple words. But it also says this word, this wording, it calls it as a weak form. So that sort of gives a precursor to the reader that there is some weakness even in this statement, but I'll like to keep that part a suspense, and we'll go along with this form for a while. Okay, so the question is, what is particle? So the starting point would be that particle in mechanics is as fundamental as point in geometry. So if you understand what is point in geometry, that is the same thing as particle in mechanics, which essentially means you don't need to understand, because yeah, you want to interrupt, because I have lots of material and some of the questions will actually get answered. Yeah, so because I am posing the questions and I will be answering myself only in the upcoming slides. So you don't need to get impatient. I'll love to take your questions at the end of the show, or maybe outside also if time permits. Okay, so would like to know what was particle in mechanics, and it is as elementary or as difficult as point in geometry. Basically, there is no definition of point in geometry. It's an abstract idea. So you can begin from there, but I'll do better actually from that abstractness, and this is where I will start from. So if the motion of the rigid body can be characterized by the motion of a single point, then it qualifies as a particle. Okay. So obviously a rigid body is a collection of large number of points. If it so happens that all the motion of all the points are identical, and I am still to define what motion is, but if it can be characterized by a motion of a single point, then it qualifies as a particle. Please note, I am still leaving the definition of point open-ended. I am assuming you are happy with your notion of point, because that was taught in primary school, you have digested it. It was not taught by a university school level teacher, so that's why you don't argue with it, right? It's only when IIT teaches you something, there's lots of argument. But point is something which school teachers have taught us, and we don't argue with school teachers at all. Very good. So for translatory motion, it so happens that the velocities of all points at every instant of time is identical. That's the definition of translation. So if all the particles in me, whether you call them cells, whether you call them chromosomes, whatever you want, all the particles at every instance of time is moving at the same velocity, then why do I worry about that infinite particles that are residing in me? Just choose one point and go ahead. So that's the crux of the matter which cracks this problem. So instead of studying the motion of many different points, study the motion of one point in the body, and that call it the center of mass. Obviously, every body has a center of mass, and you know how to evaluate that. Dumb things such as a computer also can evaluate the center of mass for you. So therefore, it's no big deal that you are replacing that infinite collection of points by a single point. Just as a matter of argument, call that point as a center of mass. Okay. So now the translatory motion of rigid bodies can be studied as a particle, because anyway all the points have the same motion as the center of mass, right? And we'll see that the equations of motions falls out with this assumption very nicely. But what are the counter examples? For rotational motion, this assumption is not true. For rotational motion, indeed the velocities of different points can be different at the same instant of time. So therefore, this does not work when the body is rotating, and in general motion, the motion can be both rotary as well as translatory. So the general motion can also not be studied using this concept. So at least we have won the day for Newton partially, in sense that for a certain class of motion, this seems to be applicable, which is precisely the translatory motion. Next, with this, we would like to revisit the notion of the laws of motion, and I call them revised, and these have been my wordings of the laws of motion, which has not come in any book as thus far, because I have not written it. Okay, but none the same, here is the first law which my teacher taught me, and when he taught me, he said that his teacher had taught him, which is called the 0th law. And I keep telling my students, please draw a free body diagram, please draw a free body diagram, and they keep forgetting drawing a free body diagram, they keep forgetting drawing the free body diagram. So it's time that we convene a mechanics conference somewhere in a resort island, and there we declare this as a 0th law, much like the thermodynamics people have done, and they have framed the 0th law of thermodynamics much after first law and second law came in. So we'll do that this winter, but before that, this is the law, 0th law. Please draw a free body diagram before you do anything in mechanics. And I put this copyleft symbol because you may think that it is my intellectual property and you would not like to copy it, but please copy it. Okay, some of you are good in copying, so don't feel shy. Please propagate this idea of 0th law. We need propagators like you in the audience who will say that yes, there is a 0th law, not given by Abhijit Sarkar or his teacher, but there is an existence of this law. Okay, after that, let us come to the first law. So first law, the way I see it now at the age of 40 years is this, that it is actually a definition of what an inertial frame is. Remember the contradiction that happened between the second law and the first law sort of asked us to relook at the wordings of the two laws. The first law, as of now, the understanding which I have now, and my understanding is very dynamic, okay, it does change, but as of now, provided my friend doesn't tip me off with this understanding, assuming that the understanding holds at least localized for some time, the understanding is this, that it is actually a criteria by which we can pick up what's an inertial frame. So if all bodies in absence of applied forces are observed to be in uniform motion or rest, then the observer is identified to be sitting on an inertial frame. And then the second law now says that in an inertial frame, the rate of change of momentum is equals to the force applied. So now there is no contradiction. The second law, F equals to ma, cannot be applied in any frame of reference, that you will agree. Because the problem is, on one side you have F, which is the force, that is just about interaction between two bodies. I slap you, you kick me, this is our interaction, okay. But this is a hard reality. I get pained by your kick, you get pained by my slap. There is nothing relative about it, but the acceleration and the velocity is relative, right? I may not see you are moving, you may not see I am moving, a third person may or may not see we are both moving. So acceleration is a kinematic quantity, definitely it is open to interpretation. Force is not, right? So the very fact that on the left hand side you have a physical quantity which is not dependent on observer, whereas on the other right hand side you have a quantity which is dependent on observer, now makes it very clear that this relation F equals to ma must hold in very specific and very special cases. And those specific and those special cases is what we qualify as inertial frame. It is a criteria by which we pick the inertial frame, and now on the inertial frame we are okay, or we are eligible to apply the second law. Okay. The third law, and this is the strong form. Here the additional issue is, other than the fact that the force between two particles are equal and opposite, we also put this as a strength in the strong form. It will act along the line joining the particles. So it is not in some arbitrary fashion. You could have 2 points and they could have equal and opposite forces in some arbitrary fashion, but the point is, if if this sort of forces do arise as action-reaction pair, then the whole world will start rotating. Angular momentum will not be conserved. So this strong form is in effect the angular momentum law, which I will come to in due course. So these are the laws of motion which gets revisited. I have now used the word bodies instead of particles, because I have now qualified that bodies can be made to look as particles, at least for translatory motion. Okay. Okay, now the question is, now that I have hopefully convinced you that what this Newton's laws applies to, the question is, well, if it applies to only inertial frame, where is the inertial frame? So I have to chase an inertial frame, I have to find an inertial frame for you, only then you will agree that Newton's law is of any good, right? Otherwise it's no good. If there is no inertial frame, you will say, that is all abstract, you are talking in some Hilbert space and Banach space, and you will be all ticked off. But let's see whether we can find an inertial frame. First question, is Mother Earth an inertial frame? Not quite, because it rotates and revolves. Rotation enough, and even if you don't go outside the Earth to see that the Earth is rotating and revolving, you can prove through experiments in the Earth that Earth is rotating. So Foucault pendulum is one such experiment which demonstrates that Earth rotates. It's again, my students will like it, that it's about a simple pendulum. It's as simple as a simple pendulum, but the only complication is it doesn't move in a plane. If you keep the pendulum as going and you just supply enough energy so that the dissipation does not take place, then you will see that the plane of motion of the pendulum keeps on changing. Okay, and that actually depends upon the latitude of the place. So unfortunately in equator this effect cannot be observed. It is observed highest in the poles, but in Paris it could be observed, and Foucault pendulum was first conducted in Paris, which is sort of midway between the equator and the poles. So the point is, I will give you examples only from the Earth. I will not allow myself to go into any Hilbert spaces which is outside the Earth, neither will I allow you to go outside any the Earth. All your questions have to be earthbound. Okay? So we will see that we can actually establish that Earth rotates. It's an experimental fact. You don't have to go outside the Earth to prove that Earth rotates. The other very important reason why Earth rotates, other very important effect of this is the clouds do get deflected. So remember what was my definition of inertial frame? If the object is left as it is, it should not move. So if a cloud is left as it is, it should not move. But monsoons happen because the clouds are moving. Okay, it not because of aerodynamic forces and whatnot. Even if there are no forces and the block of cloud just remains there, it will deflect from its path, and the reason is Coriolis. Okay, so that is again a very well studied effect. So Coriolis effect is the reason for the clouds movement, for which at least in India we have our monsoons in the right place at the right time, hopefully, except for today. So the clouds do get deflected due to the Earth's rotation. So about this question, is Mother Earth an inertial frame? The exact answer is Earth is not an inertial frame. Okay? I could have made it a little more dramatic by saying that this question actually is very interesting and we should think about it, but I'll make it plain and simple that Earth is not an inertial frame. That is for sure, because it doesn't qualify that definition. In the definition, if you remember, it's about all the bodies. All the bodies that you are thinking about and you are seeing, that should remain at rest if no forces are acting on it. But that doesn't happen for the cloud, that doesn't happen for the Foucault pendulum, so Earth is not an inertial frame. So this is the exact answer. But now my counter question to you is that, so where can we find an inertial frame? The exact answer is, I don't know. My counter question is, should we care to know? That's a very important point. There are many questions that we don't know the answer, but is this a right question for which we are trying to seek the answer? And here is my prescription. So, you this is in italics. So, on a full moon night under a banyan tree, you please perform meditation and think yourself to be in some inertial frame. There is nothing better I can offer, I am sorry, because I have told you that you will be only restricted to earth, and unfortunately earth is not an inertial frame. So, the only inertial frame is in your head. Okay, it cannot be there in earth as long as in your earth. If you are God Brahma, you can, but none of us are sure we are. So, let's just think that we can levitate into this mystical inertial reference frame. But then you will say, I should better be a Baba and join some spiritual courses rather than being an IIT. I will tell you, this actually works. Be with me. So, in that thought experiment, in that abstract and all other gullies that you can give about that inertial reference frame, please do give it, okay, because it is not real, right? But you will have to hold on to this logic that in that abstract reference frame, F equals to ma, okay. But now the point is that is this relation, you know F and you are calculating A, acceleration. So, the point is the acceleration that you calculate in this mystical inertial reference frame, which is not there, it is just there in your thoughts, is that the correct acceleration that you will get as observed from earth? That is the more important question. If you can get it, then everything actually falls in place. If you cannot, then that model of Newton's law is of no good. It falls apart, right? So, to this question, the answer, yeah. So, do we observe the same acceleration from the earth, especially now that we know that earth is not an inertial frame? That's the bottom line. This is the more critical question than the first question, that where can I find an inertial frame? Is it worth finding an inertial frame? So, the answer to this question is yes, approximately you will get it, provided that the inertia forces which that non-inertial frame is contributing is actually much lesser than the applied force. So, the mass times acceleration, the acceleration F here stands for the acceleration of the frame that you are residing in. So, if the acceleration of the frame that you are residing in is such that the inertia force which is actually playing its role in the dynamics, and here I am sort of jumping the gun with D'Alembert's principle a bit, but since you know all that, so I am assuming that you know what I am talking about in terms of inertia forces. The difference between the Newton's second law F equals to ma, and which is supposed to be applied in inertial frame and a non-inertial frame, is just in the incorporation of this inertial force. So, if it so happens that the inertial force is actually much lesser than the applied forces, then you may as well believe that the acceleration that you observe by using F equals to ma is going to be approximately. But be careful, the acceleration, even though you will make small errors, these small errors in acceleration can lead to considerable errors in position over large times, because finally displacement is half at square. Okay, half times acceleration into t square. So, even a small change in acceleration over large times t square comes in, you can have a very large change difference in the position quantities. So, unless so that actually saves the day for most of us who are not interested in time scales dynamics or motion in the time scales of 24 hours or even for that matter a few hours. Most of our dynamics experiments and robots and spaceships and vehicles are moving in time scales of minutes possibly. Our dynamics experiments rarely goes in hours, except for the people who are dealing with atmospheric sciences. For them this is therefore a very important aspect. So, with that I would like to think that I have got some understanding as of now of what this contradiction between inertial frame and non-inertial frame is, and presently I am sleeping at peace unless you disturb my sleep with some questions. Okay, by the way, this mystical inertial frame which I have seen by sitting under the banyan tree near my house is nothing but the distant star. Okay, the distant star of Newton is just as imaginary as this mystical inertial frame. And the fact of the matter is, whether in 1650 or in 2018, for all these 400, 500 odd years, you will not be able to find an inertial frame. So you might as well think that only the inertial frame resides in your thought process and nowhere else, and get going. That's the only way to go ahead. So the important takeaway other than the physics is you have to allow for certain things which exist out of the world. They are not there in the world, but it is there. You have to believe that it is there. Okay, this is my first example, and I will quickly run into the few other examples where I will bring home the same point. From particle to rigid body, as I said, rigid body is a collection of particles such that the distance of pair of points is fixed, mutual orientation of line element is fixed. Interestingly, the relative velocity between points is always perpendicular to the relative position. That happens because of the cross product between the angular velocity and the relative position. So that's all elementary. The point is the laws of motion can be written for each particle because you now have Newton's laws supporting that. The laws of motion is for each particle, but you can add them up. Before that you have to account for the interaction between each particle, and the third law gives it to you, and thereby you can derive this result that the entire body mass can be lumped at only one particle, which is called the center of mass. You concentrate only on the acceleration of the center of mass, and mass times acceleration of the center of mass is the sum total of external forces. So an oversized body like me can actually be replaced by a particle which is at my center of mass. I don't know where that is, but the point is the center of mass motion can be qualified by knowing what are the forces, external forces acting on me, and if you know the motion of the center of mass of yourself, you know the motion of the entire body. I mean, not the relative motion of it, but assuming that you are just a single body, which you are not. So this is where the application of Newton